Robot Talk is the podcast that sits down with robot enthusiasts from around the world and asks them the questions you always wanted answered. Like, will I be examined by a robot? And how does that thing work? Hello everyone! Welcome to Robot Talk. I'm your host, Claire Asher, and this week's episode is all about hands. From robotic hands to wearable hand exoskeletons that can be applied to tasks ranging from breast cancer detection to teleoperation in nuclear power plants. But first, please remember to like or rate this episode and leave us a review if that's something you can do on the platform you're listening on. And don't forget to share the podcast on social media or tell your friends about it. It really helps us reach more listeners, so thank you in advance. And don't forget to enter our competition for a chance to win your very own Robot Talk t-shirt. For more information about the competition and how to enter, check out robottalk.org. So, with all that said, it's time for me to introduce this week's guest. I recently had a fascinating chat with Antonia Tzemanaki from the University of Bristol, all about hand exoskeletons, robotic hands, and teleoperation. This week, I'm chatting to Antonia Tzemanaki, a senior lecturer in robotics at the University of Bristol, researching robot hands, hand exoskeletons, haptics, and wearable robotics. Hi Tanya, lovely to have you on Robot Talk.
Thanks, Claire. Great to be part of it.
So you lead the dexterous manipulation and wearable robotics group at the University of Bristol. So can you tell me about some of the research projects you're working on currently?
Sure. So our group is part of the Bristol Robotics Lab. And in our group, we are diving into the world of dexterous robotics, focusing on grasping, manipulation, tactile sensing, haptics, and human-robot interaction. We draw inspiration from real-world challenges, especially in healthcare and extreme environments, such as nuclear decommissioning, teleoperation in space, or handling samples from the moon or Mars. In healthcare, for instance, we're exploring robot-assisted biopsy with needle insertion, develop smart anatomical models for medical education or training. And smart here we mean sensorized or actuated. We look into haptics for surgical drilling, as well as we've been working for a couple of years now on automated breast examination aimed at breast health and empowering patients. That was called Project Artemis. What ties our project together is our commitment to human-centric research. We involve end users, surgeons, clinicians, as well as the public. Mm-hmm. We want to understand requirements and get feedback, frequent feedback, really, along the entire cycle of any of the projects we run.
Yeah, no, that's really important. It sounds like an incredibly diverse selection of projects you're working on. I guess they're all tied together by the sort of the hand.
Yeah, they are. It's all about the dexterity and the properties of the hand for this dexterity. It could be multi-finger hands, it could be multi-joint motion in the fingers of the hands. It could be a lot about tactile, because without tactile sensing on our fingertips, we probably wouldn't be able to be as dexterous as we are in the human hands. And it's all again about haptics and how do you use that to improve your interaction with a computer, with a robot. Any system really that you would need haptic feedback for.
Yeah. I mean, I've said this on the podcast before, but the human hand is pretty incredible, really, and we completely take that for granted.
We really do, and I love science fiction, and there's so many books always talking about how if we didn't have our hand in the way that we do have it, we probably wouldn't have gone past our, primeval sort of, age as humans, as a species.
Yeah, definitely. So you mentioned the project called Artemis, which is to do with the early detection of breast cancer. So can you talk a bit about that device and how it works?
Certainly. So the idea for that was, as I said, to make breast examinations accessible and frequent. For example, every 6 months, the data between consecutive examinations can be compared to try to detect any changes in the breast as soon as you can, as soon as possible. So every 6 months might not sound very frequent, but it's actually much more frequent than the current examination rate.
Okay.
So we also, we wanted the whole idea to create an autonomous platform that could open screening also to populations that don't usually attend screening. For example, placing the system in pharmacies, public areas that are easy to get to. So the device, how do we hope to do all of this? So the University of Bristol part of that project, we created soft tactile sensors that are pneumatically actuated, and by that property, we are able to change their functional range and tune the sensitivity of the sensor.
Okay.
So this allows us to sense the surface of an object, in this case, the object is the breast, or press a little bit more into that tissue, the object, and detect structures deeper within it. So if you had a little lump or a structure deep inside the tissue, our sensors would be able to pick it up, to detect it by changing their stiffness of their membrane. So the goal for all of this is to create a 3D stiffness map of the entire breast. And the other part of that project was to develop specialized, if you want to call them sensor holders, mechanisms that can do the breast examination in an efficient way.
Okay. So is it shaped like a hand?
And it's, we have two of these mechanisms. One, we called it iris because it borrows the design from the iris of a camera, the way it opens and closes. It's quite mechanistic looking, if you like. And then the other one is more biologically inspired. We called it lotus, inspired by the lotus flower, how it opens its petals or closes it, and then it's sort of soft and compliant.
Okay. I'm just imagining sort of how women might react to the idea of being examined by a robot.
Yeah. As I said, it's all about human-centric research, right?
Yeah.
So in that project, we had a constant involvement from public contributors. So we had in total, I think, 12 women that were basically following a research. We would have frequent meetings with them every few months in the project. We would show them our plans. We would get feedback from them. That was all during COVID. So you can imagine when we started, I thought, oh my God, how are we going to do this hands-on in meetings? So we actually posted materials and mock-up of our sensors and mechanisms to their houses.
Wow.
And they were able to give us feedback like that. So there were many meetings and a lot of feedback. But I suppose if I can summarize it in one sentence, it would be that they did enjoy the organic look and soft look of the lotus mechanism, because the other one looked a little bit more robotic and a little scary. But in the end, they really didn't care how it looked. They just cared. The important thing was to make sure the accuracy is as good or better than a GP, for example.
Yeah, of course. So how far along is this project? How close is it to sort of, reaching clinics?
Well, that's a good question. With everything in my field, with the healthcare robotics, we know that we're on a very, very long road.
Yeah.
So this was the initial exploration project that it was about a year and a half in total. Now we're going to go into the second phase of an exploration project for that. Basically look into it more, improve it, add to it, perfect, if you want, the prototypes, initial prototypes. And then we're going to be looking at more translational application of all of this. So we're looking probably at least 15 years, if we're lucky, down the line.
Yeah, I mean, I completely understand why these things take such a long time, but it's, I guess, an outside observer can feel frustrated that we don't have these innovations yet.
Yeah, I got the exact same frustration from the contributors that we had in the project, the public contributors. They really wanted something now, and they were so happy with what we were showing them. And they were like, "Well, yeah, why? Why would you put me in a mammography setting, which is so uncomfortable, so horrible, so painful?" They really wanted to change right now.
Yeah. But understandably, these things do take time. So last year, I was lucky enough to actually visit the Bristol Robotics Lab, which is where I came across your work. And during the tour, you were demonstrating a hand exoskeleton you were working on. So can you tell the listeners a bit about that?
Yes, we have been tinkering with hand exoskeletons for a while now. Initially designed for a teleoperated surgical robot that I was developing during my PhD. So that's at least, it's more than 8 years ago. So the key is for these exoskeletons was to incorporate multiple sensors to track all possible hand joint movements, which is especially crucial in precision grasps during surgical tasks. So that was my main interest. And so over the years, we have developed various sensors to track the fingers and their joints and the wrist as well of the hand. My favorite, however, is the ones I use Hall effect sensors. They're really, really small. They're very accurate, but they're a little bit bulky though. The whole the exoskeleton can feel a bit cumbersome and bulky. That's why I'm actually quite excited on our new soft versions of the exoskeleton, and where we are focusing on making them really quick and cheap to manufacture and custom made to fit individual hand sizes. So we're hoping to be able to show more of that in the coming months.
Amazing. I guess, yeah, it must be challenging because you want to have as many sensors as possible, but at the same time, you can't restrict the hand's movement in any way. So it needs to be really kind of, I don't know what the word is, like just not getting in the way.
Yeah, well, people have been compromising between these two things. But through my research, I found that a lot of the research for exoskeletons or even robot hands considers our finger joints coupled. But they really are not coupled. And in fact, if you're doing movements that your hand is not trained on specifically, so if you're trying to do a pinch grasp with your index and your thumb, you might find there's coupling a little bit between the two last joints of your finger here. And by coupling, I mean that basically you can predict one from the other.
Right.
So you basically only need to measure one. But this is not generally the case for the hand. And it does not apply for the middle and the thumb, or just if you do non-pinch grasps. So basically that means that we have trained our fingers to do things in a pre-configured way without us realizing it, which is really fun because I think through robotics, you can learn things about anatomy in the end.
Yeah, definitely.
So this is why I'm always insisting as many sensors as possible on the hand, on the exoskeleton, on the hand tracking system, so that then if we have a lot of information, a lot of detail about what the hand is doing, then we can then select from it possibly later. And when we transfer it to a robot hand or a virtual hand, we can then make that a little less complex.
Okay, yeah, that makes sense. So is the idea that, this would be used to control a robotic hand at the other end rather than the more traditional surgical robots I think of are kind of, arms with various implements.
Yeah. I mean, you can use the hand exoskeletons we've been making, they're basically a hand tracking device.
Yeah.
You can use them for anything you want to teleoperate something. So you're going to teleoperate a surgical instrument that is really tiny, small, and looks like a little chopstick with a little gripper at the end. You can do that. You can make a new instrument that looks more advanced and complex with little fingers, which is what I was trying to do in a PhD. You can do that. You can want to teleoperate something on the moon or, the space station. Or from the space station, in orbit to the moon or Mars, you can do that as well. So this is where we overlap with, other different fields apart beyond healthcare. So, nuclear and teleoperation space, as I mentioned before.
Yeah, I imagine video gamers would also love to get their hands on something like this.
Yeah. I mean, probably anything we use our hands in everyday life for pretty much everything. You can play piano remotely, maybe.
Yeah. I don't know what use for that would be, but I like the idea. So yeah, I mean, this kind of touches on the fact that you're applying this sort of fundamental robotics to a lot of different areas, and particularly kind of extreme and hazardous environments like space, as you mentioned, and the nuclear industry. So what different challenges do those different domains present?
Great question. Well, surprisingly, the challenges overlap more than one might think.
Okay.
The scale and nature of the objects that you handle changes, of course, but what remains constant, really, is the need for accuracy, haptic feedback, and trust in the system that you're using. And our experience on this comes again from talking to the end users. And that revealed striking similarities in requirements across all, the different industries. So we recently published a study on that. We interviewed expert operators of remote machinery from different application areas, such as nuclear, underwater operations, as well as surgeons. So we found that the requirements, as I said, are very close, apart from two. And I think this is where it was a little bit interesting. So all operators of the nuclear or underwater or oil industry and so on that we'll talk to, they wanted to have a really deep, comprehensive engineering understanding of the capabilities and limitations of their system that they were using, so that they can be able to trust it.
Yeah.
This was not the case for surgeons. They don't want or need to have a engineering understanding of that system to trust it. They basically trust the organization that provided it to them. The second one was that these systems often include delays in communication, especially when we're talking about teleoperation. If it's space technologies, we're talking about Earth, Moon, or in orbit. It could be as much as 2 seconds delay, for example. And remote operators just have to develop techniques to tackle these challenges. They have no choice. On the contrary, surgeons simply refuse to accept such a system that would have a delay, and they will basically not trust it, not use it. Which we know in 2001, I think, they did the first surgery between France and New York. And I bet there were some delays there.
Yeah.
But I haven't seen a study published about exactly how they dealt with a delay there and what they felt about it. But it would be interesting to explore more.
Yeah, definitely. Yeah, I mean, because I guess the delay is doubled as well, because you have to wait for the signal to reach the robot, and then you have to wait for the information about what's happened to come back to you.
Yeah. Yeah, and especially again, when we're talking about space teleoperation, where we have really long delays, that can be problematic, and you really have to find strategies. So we were exploring in our projects about how maybe haptic feedback could help with that.
Okay.
So we found interesting results. It can help up to a point, and then actually become so much worse. It makes communication so much worse without it, which was really interesting, and we didn't expect it, but in the end, it did make sense. Now, in surgery, if you don't teleoperate from Earth to Moon, you probably don't have these delays. So I think it's not that much of a problem because we do have good communication these days anyway in 5G.
Yeah, that's true. And I guess surgeons might feel that there's not the need, physically you can both be on the same place on Earth in theory. Whereas, if you're talking about the Moon, if you're talking about Mars, it's like, well, we can't get around that. We can't be on Mars. So you have to accept the delay.
I mean, that's why I suppose it would change if you had to operate on an astronaut from far away.
God, can you imagine?
I suppose that's why astronauts train for sort of 2 different, at least, fields and want to have a doctor on board.
Yeah.
But yeah, I mean, I get why, it's critical. I mean, breaking or destroying an experiment or breaking equipment, it's costly. Yeah. But it's not as costly as a human life.
Exactly.
And therefore, it's good. It's good that they refuse to tackle such a challenge in a way, and they don't want to have delays at all.
Yeah, absolutely. I guess the delays, maybe, you think they place an upper limit on teleoperation? So if we were talking about places further than Mars, if you wanted to teleoperate on Jupiter, that's just too long of a delay, right? This is... I don't know how long it is, 45 minutes?
I don't know actually the exact number, but I guess that this is where you wouldn't be talking about teleoperation. You would be talking at best at sort of shared autonomy, as we call it. So the operator does some part of it. The rest is done by the robot in an autonomous or semi-autonomous way. And this is really basically another technique of tackling this challenge. Try to create a shared autonomy between the system, the human, and also the other humans into the system. So we're talking about human-robot trust, but also human-human trust within that triangle of a system in a way. So yeah, in terms of how much delay is as allowed or is preferred or wanted, what's the upper limits of how much they would tolerate? That's a good question, and I think this needs more research on that.
Yeah, sure. In the intro, I said that you work on wearable robotics. Is it just the hand, or do you work on wearables for any other parts of the body?
It's mainly a hand or upper limb, at least. I decided that I'm more interested in a hand. We are also working on, for example, prosthetics.
Okay.
So this is in collaboration with other people in the Bristol Robotics Lab. Dr. Helmut Hauser.
I've had him on the podcast before.
Yeah, I know you did. Yeah, I had watched it. So Myra, our PhD student, she's working on developing soft sensory skin, which is really interesting. And the goal for that is to use it to decrease the rejection rates of prosthetics. Again, inspired by a healthcare challenge, but really doing fundamental research on developing new novel sensory techniques and soft skins, which is really cool.
Yeah, that's awesome. I'm constantly amazed by the things that people are doing in these kinds of areas.
Yeah.
Tonia, it's been fascinating speaking to you today. I've been talking to Antonia Tzemanaki, a senior lecturer in robotics at the University of Bristol. Thank you.
Thank you very much. It was great to be here, and thank you for the invitation.
Thanks for listening. If you enjoy Robot Talk, I'd really appreciate it if you could share the podcast and leave a review to let us know what you think. And if you've got a question you'd like me to ask one of my future guests, you can contact us on social media at Robot Talk Pod or visit robottalk.org. We regularly announce upcoming guests, and I'd love to include your robotics questions, whether they're super basic, a bit silly, or even quite profound, in my next interview. Next week, I'm speaking to Andrew Starr from Cranfield University, all about robot maintenance and railway inspection robots. Until then, I've been Claire Asher, and this has been Robot Talk. Robot Talk is brought to you by the Hamlin Centre, Imperial College London.